Hey everybody, welcome back to our discussion of image formation by reflection. And what we're going to do in this video is look at how curved mirrors can form images, and specifically spherically curved mirrors. So these mirrors, their surfaces, their reflecting surfaces are parts of spheres. Now you don't have to necessarily have a spherically curved mirror to form an image, but the analysis of non-spherical or aspherical mirrors is a little bit more complicated, the ray tracing. So we're just going to stick to curved mirrors. And I will add that while it's really cool to look at how these images are formed, I'm not going to test you on curved mirrors. So you should know some things about plane mirror image formation, but this is just for your enjoyment. To see how these spherically curved mirrors form images. And I have a video demonstration I'm going to show you at the end of near the end of this video, and also when I see you in person we'll take a look at curved mirrors forming images too. Okay, so just sit back and enjoy. Now on this slide, this is going to establish some things that are important in figuring out the imaging properties of these curved mirrors. And what this one shows is what's called a concave mirror, and that's to be contrasted to a convex mirror. And I find that terminology can be confusing. So the way I try to remember this is, okay, when we do these ray traces, we're sending light in from the left traveling to the right. So imagine you're standing over where the light is coming from, right? You're standing here on the left side of the mirror. For a concave mirror, you're looking into the cave. So you're looking into this cave, okay? If this was a convex mirror, just imagine turning that mirror, flipping that mirror around. So if this was a convex mirror, it would look like this. So here is your optic axis. Your optic axis is right here, this line right there. See, if you're over here and you're looking this way, that would be called convex. You're not looking into the cave, okay? All right, now, get back to the concave mirror down here. All of these mirrors are going to have what we call a focal point, and that's symbolized by uppercase F. Now, it turns out what determines that focal point is going to be the shape or the curvature of the mirror. And that can be characterized by something called the radius of curvature, uppercase R. And the way you find the radius of curvature is, again, this is part of a sphere, right, in 3 dimensions, this curved surface. So in 2 dimensions on your screen, it looks like it's part of a circle. Well, this point right here, this big C, that's the center of the circle. Or in 3 dimensions, it would be the center of the sphere. Okay, so the radius of curvature is just the radius of that circle or sphere. Well, the radius of curvature is going to determine the focal point. Okay, now what exactly is the focal point? Okay, so as shown here, if you take a beam of light, so-called collimated rays, see how all these rays are going to the right? They're all parallel to the optic axis, right? And they're all parallel to each other, right? Okay, that's redundant, but they're all parallel to the optic axis. Those rays, if you do or look at the reflected light, you'll find out that all those reflected rays actually intersect at this point on the optic axis, and that's called the focal point. It's a really good reference point for figuring out where images are going to be formed. And people can get confused because a lot of times people think, oh, the focal point, that's where the image is always formed. No, it's not. The focal point is where these collimated rays would get focused to if you sent in collimated rays. But when you form images, you're not using collimated rays, right? The rays are going to be not parallel that form the image. So the image is going to get formed somewhere else. But the focal point is a good reference point for helping to figure out where that place is that the image is formed. Okay, so all these rays will get intersect through the focal point. Now, one thing this picture doesn't show, which I wish it did, is it doesn't show the continuation of these reflected rays. So it looks like all these rays just get sucked into the focal point and disappear, but they actually continue traveling. So they just don't show it. So this ray is going to keep traveling that way, and this ray is going to keep traveling that way, and this ray is going to keep traveling that way, and this ray is going to keep traveling that way, okay? But it's that intersection point that's of interest, the focal point. Again, it's a reference point. Oh, and before we leave this slide, because I don't have a picture of this, you might ask, well, for a convex mirror, what determines the focal point? Yeah, that's a good question. So look up here. If I were just to show this ray going like this ray, by the law of reflection, is going to reflect like that. Because again, if I were to draw a surface normal, it would look something like this. Right? It has to be perpendicular to the surface right at that point. So you can imagine, right, if you have this sphere, there is a point that's actually tangent. There's a surface that's tangent to the sphere right there. Okay? And so you could draw a line perpendicular to that surface, and that would be the surface normal. So this angle of incidence has to equal this angle of reflection. So that ray would go like that. If I were to draw another ray like here, it would go something like this. Well, if you trace, see how when these rays leave the reflecting surface, they're getting farther apart, they're diverging. If you trace them backwards, they will appear to come from a common point on the optic axis. And that is how we would determine the focal point for a convex lens. Okay, so again, these are good reference points. And I'll show you that in the next slide, why I say that. So the first case we're going to look at is a concave mirror where the object, this blue arrow, is outside the focal point. So in other words, look, this mirror, based on its curvature, it has a predetermined focal point. You see it right there, that black point right there, labeled with big F. Okay, now, if I put the object to the left of that point, that's what I mean by outside the focal point. Oh, you know what? I just remembered. I'm sorry to do this to you, but I should have completed this slide and said, look, there's something called the focal length, and that's symbolized by lowercase f, and that's going to be the distance from the mirror on the optic axis, that point of intersection, to the focal point. So this distance right here would be the focal length, okay? You'll hear that again when we get to lenses, the focal length, and it'll be a very important quantity when we look at image formation by lenses. Okay, so getting back to this, the object outside the focal point means it's to the left of the focal point. Again, we always trace the rays from left to right, starting with the object on the left. So outside means to the left, okay, in this picture. If that's the case, it turns out you always are going to get a real image. It's going to be inverted or upside down, and it's always going to be smaller than the object. And to see that, this picture traces some rays. Okay, so let's look at the rays that that are traced here, and then I'll tell you what I would do if I were doing the ray trace. So the first ray that they have drawn in this picture is from the tip of the object. We always are going to image the tip of the object, and they draw this orange ray which is parallel to the optic axis. Well, by definition, that has to be reflected through the focal point, because any ray that's parallel to the optic axis is going to get reflected through that focal point. So there you see that reflected ray going through point big F. The next ray that they draw is this purple one that goes through the focal point. Well, if you do the reflection there, that turns out that reflected ray is going to be reflected parallel to the optic axis. So any ray that goes through the focal point will end up getting reflected parallel to the optic axis. And then the last ray that they draw is one that goes through the center. Well, it turns out any ray that goes through the center is going to hit the mirror at normal incidence. So that would be the surface of the mirror. So this blue ray is coming perpendicular to that little surface there. Okay? Again, you can think of a plane right there that's tangent to the curved surface right there. So that blue ray is going to bounce or reflect right back upon itself and go right back through the center. So they have three rays leaving the mirror. This ray, this purple ray, and this blue ray. If you look, you'll see that all three of those rays are converging. In fact, they meet. Where do they meet? Right at this point here. And that, my friends, is going to be the tip of the image arrow. So then you just draw the arrow in, starting from the optic axis. This time it would be upside down to that point right there, and there's the yellow image arrow. Okay? So you can see that it is definitely real because it's converging rays, which means if you actually put a piece of paper there, you would see that image on the paper. Now, there are some caveats. First, you have to have enough light coming from the object to actually see the image on the paper. And when you put the paper there, you can't block, right, all the light coming from the object. So I couldn't put a giant piece of paper there and expect to see the image there. You got to let some of the light hit the mirror. Okay. It is inverted, which just means a fancy way of saying upside down compared to the object, and it's always going to be smaller. Okay, so it doesn't matter as long as where the object is, as long as it's outside the focal point, you're going to have real inverted, smaller image. Now the size of the image will change with the object distance. So as I move this blue arrow around, the location and size of the image will change, but it's always going to be real inverted and smaller than the object. Okay, and I'll show you an example of that in a video demonstration at the near the end of this video. Okay. I wanted to talk about the two rays that I would draw, because you only ever need two rays to figure out what's going to happen for an optical system. And you'll see when we do lenses, we're only going to draw two rays. So I would draw the orange ray for sure. I always draw a ray from the tip of the object parallel to the optic axis. But the other one that I would draw would be from the tip of the object to the intersection point of the optic axis and the optical element, in this case, that curved mirror. Now, it's going to be hard for me to do this. I'll do my best. But I would draw a straight line like that. That would be the ray, the other ray that I draw. I wouldn't draw the purple and the blue one. Okay, so if we apply the law of reflection, the optic axis is actually the surface normal in this case. So the surface normal is this line. That angle is going to equal the reflected angle. So that angle. And see, this reflected red ray is going to go right through that common intersection point with the orange ray. Okay, so I would draw the orange and the red ray to get the location of the image. Okay, now let's actually move the object inside the focal point. So you can see in this diagram, this picture, I now have the blue object arrow to the right of the focal point, in between the focal point and the mirror. That's what we mean by inside the focal point. Okay, so if we did the same three rays that we did before, the orange, the purple, and the blue, they would look like this. Orange ray would reflect through the focal point because it's parallel to the optic axis. Purple ray, if it's coming from the focal point, as if it came from the focal point, it would reflect horizontal to the left like that. And this blue ray, if it appears as if it came straight from the center, it would leave the object arrow right here and reflect right back upon itself. Those three rays, you can see as they're leaving the mirror, they're diverging, they're getting farther apart. So what we do is we trace them backwards from where they leave the mirror. So we trace the purple one back this way, the blue one back that way, and the orange one back that way, and they all appear to come from a common point, which is right there. That is the tip of our image arrow. Now we just draw the arrow in, boom, down to the optic axis, and we got it. Okay? If I were to draw that ray, the second ray that I always draw, it would be this ray. I would always go from here to that point right there. Oh my gosh, right? That's supposed to be straight. And then it would reflect like this, so that this angle and this angle are the same. And I didn't do a very good job. But if you trace this ray backwards, it would appear to come from right there. So this ray actually should be more like this, not this one. Okay? Again, it's hard for me to do a careful ray trace with my stylus. Okay, but in any case, if you have a concave mirror and the object is inside the concave mirror, you're always going to get a virtual image. It is upright or not inverted. It's not upside down compared to the object, and it's always going to be bigger than the object. You get a bigger image compared to the object. Now, in order to see this image, this is a good question, your eye or a camera lens has to catch some of these diverging rays. So your eye has to be out here looking into the cave, and your brain is going to see that. Okay? Okay. Now, the other case that we can look at is, what if you have the mirror turned around so that it's convex? Well, it turns out it doesn't matter where you put the object. You will always form a virtual, upright, or not inverted image that is smaller than the object. And it's always going to appear over here behind the mirror. And these just do the ray traces, the same 3 ray traces. You can, I'm not going to go into detail there. You can trace these if you want. You should see that these rays are diverging as they leave the mirror. If you trace them backwards, boom, they appear to come from right there. So that's where the image is going to be. Now, if I move this object closer to the convex mirror, yes, the location of the image and the size will change. In fact, it'll get bigger and bigger and look closer and closer to the mirror, but it's still going to be virtual, upright, and smaller than the object. Okay? All right. And I think I want to show you I want to show you the video of these 3 different scenarios. Okay? And I'll also show you in person when I see you. I'll bring this mirror in that you see in the video so you can have a better look. But let me go ahead and end the show and go to my other PowerPoint where I'll run the video. Okay, so you can see right now I'm just holding this mirror, and this is part of a sphere. In fact, this is a hemispherical mirror, so it's actually half of a sphere, the surface. And I'm going to first turn it, let me go ahead and play the video, so that it's concave with respect to you. And right there, let me just stop it right there. You can probably see that's me, a much younger me, but that's me. See, I'm upside down. So what you're looking at is I am the object. I am outside the focal point. The focal point of this hemispherical mirror is actually very close to the center. In other words, let me back this up and pause it. The focal point is actually here on the optic axis. It's very close to the actual surface. Okay? So I'm definitely outside the focal point, and what you're seeing is the real image of me. There it is right there. That is the real image of me. I am inverted. Right? You can see my head's down here and my body's up here. And the image is smaller than the object, okay? And you might even see my friend Harsh is right here. Harsh did the video recording for me, okay? But that is a real image formation with a concave mirror. Okay, now I'm going to turn the mirror so that it is convex with respect to you, okay? Okay, now I paused it. What you're seeing is, now you're seeing a virtual image of me, and that's Harsh there. It's sort of hard to see him, okay? But that's a virtual image of me. So it's upright, it's not inverted, it's not upside down, and it's smaller than the object, which is me, okay? And then I'm going to turn it back around so that it's concave again. And now I'm going to take my finger and put it inside the focal point. Now it's going to have to get really close. So let me just pause it right here. I'm bringing my finger in towards the mirror, but it's still outside the focal point. So you can see over here, you see a real inverted image of my finger. I'm going to have to get my finger really close to the surface because, again, this focal point is close to the surface. But Let me just do that. And at some point, you should see a big upright image of my fingertip. Oh, right there. See it? Right over here? Whoop. See, it might be hard to tell, but it is not inverted. It's upright. And it is a virtual image. Okay, so it's sort of hard to see there. But that's it right there. It's better in person. And you can still see the upside down version of Harsh right there. That's the real inverted image. Okay. Anyway, it's fun to do this with mirrors. Okay. All right. Look, what I'm going to do is I'm going to stop this video, but I invite you to play the last video, video 3 for this part, because I'm going to show you a video of some optical illusions using mirrors. I'll also show them to you in person, and they are better in person, but they work okay in the video. So, all right, I'll see you then. Bye.